So we're in 8th chapter, Earth as a Planet, Astronomy 1. In this chapter, we'll start with a global perspective of the Earth. Describe components of the Earth's interior and exterior, and see how scientists determine the structure of the Earth, the layers of the Earth. And within this section, we will also look at the magnetic field that surrounds the Earth, how that magnetic field is created, and how that magnetic field help us protect from the um, charged particles from the solar wind. Thinking ahead, in this chapter, in general, we will examine the composition and structure of the um, Earth's surface and core. Uh, Earlier, when we studied other planets and moons, we know, for example, this moon, it has multiple craters in it. The Earth's surface does not have that many craters, partly because the Earth's surface is very active, very dynamic. We get lots of rain, hurricane, wind, volcanoes, and that all that atmosphere, you know, uh, makes these craters go away. And plus, we don't have that many heavy bombardment as we used to. So basically, the Earth's atmosphere and the dynamic activity on the surface of the Earth, has taken away the craters it may have in the past. This is our planet Earth. This photo was taken, I think it's the first image ever taken of the Earth from outside or up from the space that showed Earth as a spherical round ball, and it's called blue marble. It was named blue marble. It was taken by Apollo 7 astronauts. It is approximate diameter, 12,760 kilometers. Um, Heavy elements such as iron, silicon, and oxygen are its major composition. Its orbit is nearly circular, orbit around the sun, and the temperature is just right to support liquid water and hence to support life. I've written life in the parenthesis code because life, as we know it, mostly the advanced form of life, um, and partly because why Earth can have liquid water and has right temperature is due to its location from the sun, due to its distance from the sun. It is at the right distance. We call the Goldilocks zone or habitable zone, where water can remain in liquid state. If it is too close to the star, the water gets evaporated, and if it's too far from the star, all that water is in the form of thick ice sheet. So there cannot be any liquid water. So we're just at the right zone. And here are other information on the uh, orbital parameters, semi-major axis, 1 AU period, 1 year. We define that for the Earth. That's our standard unit, the Earth-Sun distance, or the distance from the Sun to Earth is defined at 1 AU, and all other planets are defined with respect to this 1 AU distance. Period is again 1 year in terms of uh, the rotation period is close to 24 hours, but not quite 23 hours, 56 minutes, and 4 seconds. Density is about 5.5 gram per centimeter. one of the most dense planet in the solar system. Now the Earth's interior, or it starts from the crust. It has different layers due to the differentiation process. When it was in more molten state in the early days, it was not all solid like this, and the heavier elements started to sediment towards the bottom and form these kind of layers by the differentiation process. And now we know that Earth has an inner core, core and inner core, um, and outside of it is the mantle region, and the outside, what we are familiar with, uh, what we see every day, and what we get to touch and feel is the crust. And one thing, how we know these things, it's very hard to probe down there and see. We don't have such equipment to actually get into the core, but the scientific method called seismic wave uh, um, studies, help us to reveal the different structure of the inner core of the Earth. It's like the acoustic waves are sent inside, and how they interfere with the certain materials of the core determines how they get reflected back, or pass through, get on the other side. And by analyzing the incident wave versus outgoing waves, the difference between that help us create a picture. Sometimes those waves are reflected back, and we can also create an image. The ultrasound of a baby when they are inside mother's womb, it's a similar technique. We send low frequency, very low energy, because we don't want to hurt the baby. Very low energy waves are sent inside, and as the different parts of the baby reflects back the wave, and that wave is transformed into an image, reanalyzed to form an image. Similar technique, seismic waves technique, help us understand, see what are inside the Earth. So topmost layer is the crust. That crust can be divided into oceanic crust, continental crust, landmass. Underneath the ocean, these are oceanic crust. 55% of the Earth's surface is oceanic crust. Quite shallow, only 6 kilometers thick. Then the mantle starts. These oceanic crust are composed of uh, basalt rock made up of silicon, oxygen, iron, aluminum, magnesium, these heavy metals. And the continental crust, the landmass, is 45% of the Earth's surface. It ranges from 20 kilometers to 70 kilometers thick. In the mountains and hills have higher thickness, and mostly composed of silicon and oxygen. Of the total Earth's mass, the crust, both of these only makes up about 0.3%, and has a average density of 3 gram per centimeter cube. So you can see that majority of the mass are underneath the crust with higher density. Because they have higher density, they tend to sink towards the center, like here. And the crust is about 3 gram per centimeter cube. The average of the whole is about 5, so we can see the material underneath have more density. This is the satellite image, radar mapping of the whole Earth's surface, flattened out map, of course. and you can clearly see the land mass and the ocean mass. The blue is the ocean, and even within the ocean, this dark color represents the depth, higher depth. This is the Pacific here. This is Pacific region, South Pacific, the Atlantic, um, and the landmass. This is Greenland and the Antarctic in the white down here. This is the Earth's crust. And underneath the crust lies mantle, this grayish region here, largest region of the Earth, depth up to 2,900 kilometers. This is not exactly solid or liquid. It's under pressure, this solid can deform. So it's more or less solid, not exactly hard solid. A density between 3.5 and 5 kilograms. And these mantle region here have active plasma regions where it can eject, active magma region where it can eject magma out as volcanoes. And we'll look into volcanoes in a minute. So the innermost is the core. It has two regions, inner core, outer core. In outer core is mostly liquid, iron, nickel, sulfur, ions of iron in the ionized form or non-ionized form, outer core liquid. And inner core, we haven't understood completely, but it's mostly solid, and have the highest density materials because it's at the bottom, and high density materials tend to sediment more towards the center or at the bottom. That's the Earth's interior. So it has crust, mantle, core. Core can be divided into inner core and outer core. And another important feature, property of the Earth is its magnetic field. Earth acts like a magnet. You've seen a magnet, a bar magnet has, its magnetic field around it. The field, it's originate at some pole, and it goes to the other pole, and it doesn't end there. These lines here, they go from inside of the magnet and comes out from the north pole again. So if this is south here, the field line, this field line is originating here, goes to south pole and comes back again, or the one that's originating at south. Uh, um, it doesn't end at each of these poles as the diagram shows. Here I can draw, and these lines continue within the magnet. So this line continue, they never cross each other, but they continue inside of the magnet, and they always form a closed loop. That's the main property of the magnet. And that's one of the reasons the magnets cannot come with separate poles. Magnet cannot have a separate north pole and a separate south pole. That's one of the biggest questions in nature. Charges, I can have a negative charge and positive charge separated from each other, but the north pole and the south pole cannot be separated. They are, no matter how, if you cut a magnet into half, you always get north and south, no matter how small you cut. Okay? And similar to a bar magnet, our Earth behaves the same way, as if it's a bar magnet. It has north pole, south pole, magnetic field lines. It's imagine in 3 dimension. Here, the magnetic originating from north and ending at south, and they go from inside and form a loop. So it has this donut shaped magnetic field surrounding the Earth. Where does that come from? That's again one of the biggest questions. We think we know the answer. The Earth's magnetic field. So this core region here is in liquid state. It has liquid iron in ionized state. And what we know from our general current and magnetism rule is that whenever charged particles move in a wire, like this wire here, or this one has a current in it, so this has a charged particle moving through it. Whenever charged particles move in a wire, it generates magnetic field around it. We have tested and it is proven. If I place a compass magnet around the wire, that compass deflects. So what that tells is the moving charged particles generate magnetic field around it. So since there are charged particles inside of the Earth's core rotating, as Earth rotates, these charged particles generate this huge magnetic field that envelops, that covers the Earth's surface, or the whole Earth, in this region called magnetosphere. And this magnetosphere, what it does is the charged particles that are brought up by the solar wind sends out this plasma charged particles, and when these charged particles get closer to our magnetosphere, it creates this tail here because there's a shock hitting our magnetic field, creates this shock here, as you can see. And also the charged particles can or actually these charged particles swirl around the magnetic field, and they get collected in these regions called Van Allen belts. These magnetic charged particles get collected in the regions called Van Allen belts. So these are high energy ions regions here. And when these charged particles are guided by the magnetic field, as you see, the magnetic field lines end at the south pole and the north pole. So all these charged particles, when they hit this magnetic field, the charged particle go or encircle in the helix shape, and they're all guided towards the north pole and south pole. And as they enter the Earth's north pole or south pole, the charged particle ionizes the molecules in the atmosphere, and that causes the auroras, or the northern lights. And so that's the overall global perspective of the Earth's surface and the magnetosphere. Next is the Earth's crust. What are different types of material that make up of the Earth's crusts? There are plates, tectonic plates, that we'll look into it. We'll also see the difference between rift zones and subduction zones. Then we'll see how mountains are built, formed, and the effect of volcano on the Earth's surface. The composition of the crust. We know the Earth is a very dynamic place. we have recorded live volcanoes, and this one recently happened 2022 115, the past January. You may have seen in the news. This was um, taken by a satellite. It's a satellite images stacked together in the form of a video. A calm ocean, suddenly a volcano from underneath, erupts, these sending plumes of lava, gas, and smoke up in the sky. Along with that, it brings up all that material from the mantle region of the Earth. And um, uh, here it cannot be seen, but I'm pretty sure there is a small island formed underneath. It was somewhere in the South Pacific. Okay, and so like I said, the Earth's surface is very dynamic, geologically active place. Not just this, we have hurricanes that move lots of material. We have tornadoes, and most importantly, the erosion. When erosion happens for hundreds of years, millions of years, if you have been around uh, uh, Arizona, Grand Canyon, you will appreciate the sheer effect of the erosion. This one here is more than 1,000 feet uh, carved by Colorado River, and that's how Grand Canyon was formed, the largest canyon on Earth. I mean, this is 1,000 feet as it goes down. This is Horseshoe Bend above Grand Canyon in Page, Arizona. The actual Grand Canyon is much deeper than this, and this is all by the Colorado River, the erosion caused by the Colorado River as it takes away the soft soil downward, carving it down and in the sides. The other object, Earth is the most active. However, the Jupiter's moon Io has lots of volcanoes. This volcano spits out like this internal metals, some in the charged form, in the ionic forms, and it has a lot of ions in its atmosphere. Continuing the composition of the crust, we basically find three types of rock. Uh, the major um, division, the igneous rocks, the sedimentary rock, and metamorphic rocks. If you're in a geology class, I'm sure you can further break down these igneous rock into 10 different parts. But we are just looking in general. Uh, the oceanic basalt and the continental granite are the igneous rock, and they're mostly formed by cooling of the lava. When they're in molten state, they come from underneath the surface, from the magma vault when the volcanoes push them up, or when two tectonic plates collide, these things can come up. We'll look into tectonic plates in a minute. So these cool down uh, lava from volcanoes are examples of igneous rock. The sedimentary rocks are formed by the fragments of either igneous rocks or could be some biological materials. When they get deposited under the water or on the land, one after another stacking together forms these sediments, and with enough pressure, they turn into rocks. Like sandstone shells, limestones, these are sedimentary rock. And sometimes with enough pressure and temperature, the sedimentary and igneous rock can physically or chemically change its features, forms. Those are the metamorphic rock. Primitive rocks are the rocks that, the building block of the solar system from the in the primitive material. the time when the solar system was formed. But we don't have such material on the Earth. They have all transformed into something else. Some of the comets or asteroids are formed with the primitive rock because they have not been transformed into any other forms. So the composition of the crust are mainly igneous rock, sedimentary rock, and the metamorphic rock. How does the whole crust looks like? It's very dynamic, it's moving, and it's not one piece. That's the key here. Plate tectonic is a theory or an idea that explains, how slow motions within the mantle of the Earth move large pieces, large bodies, like a puzzle here. It's a section here within the red line is a piece of puzzle. These puzzles are put together and form this world map. And here, within this red line here is a fault. It's a fault line. If these black arrows are pointing away, so that means this plate and this plate, at that point, these plates are moving away. And if you see two black arrows pointing towards each other, like here, these plates are coming together, they are colliding. And there is one interesting thing here, right on top of California. These are anti-parallel lines, so the two plates are moving, sliding away from each other. This the the Pacific side is moving up, the land side, the eastern side is sliding down. We call this region here the San Andreas Fault. And this has consequences. It can create new land masses. A simple plain mass can be raised up in the form of mountains, or sometimes everything can collapse. And whenever things like here, San Andreas Fault, when they grind with each other, sometimes that pressure is hard enough to shake the earth. And that happens a lot, especially around San Andreas Fault. That's why we get lots of earthquake around the California region, the west of the Rockies. So the Rocky Mountain is right here, and as you can see, the east of the Rocky Mountains are more stable. There's not much tectonic activity that goes around here. So that's why the eastern part of the U.S. did not get much earthquake. The land is very stable. As a matter of fact, the first major or measurable earthquake in New York was in 2011 summer. Because I was there working in a lab, that earthquake happened in 60 years. But other fault lines like the San Andreas Fault, and look where this Japan Trench is. There is another, the two plates colliding here along this line, and that creates hundreds of earthquakes a year around Japan. And there are many more. Here, this Philippine plate and this Australian Indian plate here, that causes lots of underwater earthquake and volcano. Remember the tsunami, the biggest tsunami in Japan and in Indonesia, caused by these moving tectonic plates. And there are two types of zone, rift and subduction zone. When these tectonic plates move apart from each other, create a hole like this, and the magma from underneath blow out as volcanoes. In the subduction zone, for example, here this is the Indian plate. The top one is the Eurasian plate. They are kind of colliding each other, and the Indian plate is going down and pushing the Eurasian plateau higher up, and that has created the Himalayas here. This is the Himalayas here. This is Indian plate. This is Eurasian plate. As this thing goes underneath, this pushing the Eurasian plate higher and higher, and the Himalayas are born. So about 71 million years ago, the Indian landmass was here, 75, 55, 38, 10 million, and at now it has basically merged with the Eurasian plate up here, and as a result, Himalayas are born, the highest mountains on earth, right here. And even today, I was there in 2018, and I found these shells that are only found on the ocean bed. So you see, previously it was all ocean, and so it's raising the ocean bed in the form of mountain, and all that shells, organisms, they sediments get trapped between the sediments, and by erosion, other phenomena, those they get exposed, and you find these hard shells. And this is the another fault zone examples. This is the San Andreas fault. It is visible, quite striking. And these plate boundaries, the tectonic plates, they are marked by such cracks on the Earth's surface. This is the largest fault line, San Andreas fault, hundreds of miles, runs from South California to North California. And these are grinding each other in anti-parallel way, and it's believed that these two plates will slowly separate and move away from each other. In few million years, Los Angeles may be an island off the coast of San Francisco, so it will move into Pacific. And lastly, the volcanoes. Volcanoes can be destructive to wildlife, even to human beings. At the same time, they're constructive in a way. Many of our land masses are created, mostly islands, by volcanoes. And it is very visible. If you've been to Hawaii, or if you ever plan to go to Hawaii, now you'll see there are 4 major islands. Big Island here, Oahu, Kauai, Maui, or maybe Maui, Kauai. But these are 4 major islands, and this is the Big Island is still active. When I was there, I could see red plasma, lava coming out. You'll see smokes venting out from holes everywhere around Big Island, and this it brought up all these magma, the lava from the bottom of the Pacific, and raised up so high it formed the Mauna Kea. Mauna Kea is the highest mountain. If you measure from the surface, bottom of the ocean, that lava brought all from the bottom and rose about 9 kilometers from the surface, from the ocean floor. And the tallest mountain, Mount Everest, is measured from the surface, from the sea level, and that's 8,850 kilometers. But this is 9 kilometers measured from the surface, ocean floor. So I guess that's the difference. And this is how some of the islands, land masses are formed um, by volcanoes. Okay, I will stop here. Next, we'll look into Earth's atmosphere.